Now in this lesson we will solve the scattering of a circular infinite cylinder, and we will obtain the analytical solution. Since this is a canonical geometry, remember this is a typical two-dimensional case in which we have infinite an infinite cylinder along a z direction. Okay, so that the boundary condition, the boundary condition is in a surface of constant radial coordinate rho, radius rho equal to a, is the coordinate of the surface, rho equal to a. So when the incident field is also have invariance along z direction, also the incident field is constant along z direction, because the incidence is normal, the direction of incidence is normal with respect to z direction, then clearly the incident field is also constant along z, and then everything is constant along z. The boundary condition, the incident field, so the field and the scatter field will be also constant along z direction, the current will be constant along z direction, and then we can just define a problem in x and y coordinates, that is a two-dimensional problem. This is the typical two-dimensional case. You already know that. I briefly introduced the two-dimensional case in chapter 3 about numerical methods, and also you solve the two-dimensional problem in practical project 2, so you already know this. And we have to distinguish between two polarizations. When the electric field is transverse to z direction, z is the direction of the axial symmetry, so z is electric field tangent to z direction, that is, the electric field is in the plane, in the xy plane, that is the plane perpendicular to z direction. The other polarization, the TM case, is transverse magnetic with respect to z direction, that is, the magnetic field is transverse or perpendicular to z direction. We will obtain the canonical solution following the book by Konstantin Balanis. This is Advanced Engineering Electromagnetics from Balanis, is one of the books that we recommended in the bibliography of this course. It's a very good book, a very good reference book, and we will follow the solution only for the TM case, which is the easiest. And I will only highlight the main steps and the equations that we obtain, and will not explain in detail the whole procedure, because you already have the whole procedure explained in the book. So we start as always. We start with the incident field. The incident field is a plane wave traveling along x direction, so it is perpendicular to the z-axis and constant along z direction. We will represent the plane wave, the exponential, in polar coordinates, so x becomes rho cosinus theta. And now we use the wave transformation to express this exponential in terms of a summation of Bessel functions that are cylindrical wave functions, and we get this. This is one of the wave transformation that I already presented in the previous class. And we can also obtain the magnetic field, the incident magnetic field, as the curl of the incident electric field, as we can see here. Now, we have to apply the boundary condition to the total field. The total field is the summation of the incident field plus the scatter field, where the scatter field is the field due to the equivalent currents in the surface of the scatterer that I have said before that in the case of perfectly conducting cylinders like this, the equivalent currents are the same as the induced current, electrical induced current in the surface of the cylinder, and the equivalent magnetic current is zero because the tangent component of the electric field is zero due to the boundary condition in a perfect conductor. And now we already have the cylindrical wave expansion of the incident plane wave here, and we need a cylindrical wave expansion for the scatter field. And since the scatter field is due to the currents in the surface of the cylinder and it travels outward the cylinder, we can represent the scatter field as a summation of cylindrical waves with outward propagation, and these are the Hankel functions of the second kind. So this is the cylindrical wave representation of the scatter field where the coefficients Cn are unknown. The coefficients Cn are the weights of the cylindrical harmonics, the cylindrical outward traveling waves, and these are unknown. We have to find these coefficients so that the total field agrees with the boundary condition. So we set the boundary condition here. The total field, the tangent component of the total field is equal to 0. Since we are in a TM case, the electric field is already parallel to z direction, so it is tangent to the surface. So in fact, the z component of the electric field, which is the component tangent to the surface, is already the whole electric field. Okay, so the tangent component of the total electric field equal to the electric field itself is at the surface evaluated at rho equal to A, which is the surface of the scatterer, is equal to 0. If we write the total field as the incident field here, we have the incident field here and the scatterer field here. For the incident field, we already know the cylindrical wave expansion, which is given by the wave transformation, and for the scatter field, we have a linear combination of cylindrical harmonics with outward propagation, that is the Hankel functions of the second kind, which with unknown coefficient Cn. Here we can isolate the unknown coefficient Cn, and we obtain that the unknown coefficients must be equal to this quantity, to this formula, for the boundary condition to be true. And now that we already know the coefficients, the Cn coefficients of the scatter field cylindrical wave expansion, we substitute them in the formulas of the total field or the formulas of the scatter field and obtain the value of the scatter field and the total field. In this case, we substitute these coefficients that are here. These coefficients are here. These are the coefficients. Okay. We substitute the coefficients in the formula of the scatter field. Remember that these were Cn. Okay. And since this it is the coefficients of this expansion have even symmetry. Since they have even symmetry, we can represent this exponential Fourier series as a cosinus Fourier series in that way, which is more convenient because now we start the summation from 0. We obtain the magnetic field as the curl of the electric field also for the scatter field, and when we sum the incident field plus the scatter field, we get the total field, that are the fields here enclosed in the red rectangle. These are the formulas of the total fields. Here we have solved the problem of the plane wave scattering of infinite circular cylinder. In practice, it has been very easy. It is probably the easiest canonical problem to solve for an analytical solution. These are the fields, electric and magnetic total fields. We can also obtain the equation for the induced current, because remember that the induced current is the tangent component of the magnetic field evaluated at the cylinder surface, which is rho equal to A. So here in the phi component of the magnetic field, because the phi component is the component tangent to the surface, the magnetic field is transverse magnetic, so the magnetic field doesn't have a set component. It only has rho and phi components. The rho component is perpendicular to the cylindrical circular surface, so it is the phi component which is tangent to the surface. So we set the boundary condition for the phi component, that is the current is the tangent component of the magnetic field, that is essentially the phi component of the magnetic field, but now the current is oriented along z direction. So it is this. But here we have some derivatives of the Hankel functions, and we can use the Wronskian, which is a formula relating basis functions that you can find, for example, in the appendix dedicated to Bessel functions in Balany's book. You can find this equation for the Wronskian, and using it you can easily replace remove the derivative of the Bessel functions and get this formula for the tangent component of the magnetic field, the phi component, which makes the induced current equal to this formula, which is a simple formula giving the current in the surface of the cylinder as an expansion of cylindrical Bessel functions. We can do some approximations in special cases. For example, when the radius of the cylinder is much smaller than lambda, then here we have beta times the radius is 2 pi times the radius over lambda. So if the radius over lambda is very small, then we have a very small argument of the Bessel functions, and the dominant, in this case the dominant Bessel function is the order 0. All the other Bessel functions, when they are evaluated at very small arguments, become very, very small, much smaller than the Bessel function of order 0. So this is the dominant term. But here we can also apply an approximation for the small argument approximation for the Bessel functions of first kind and second kind, that are the real and the imaginary part of the Hankel function. And in fact, for very small arguments, the Bessel function of the first kind is approximately equal to 1, and the Bessel function of the second kind is almost infinite, in fact given by a logarithm of a very small number that you know that goes to minus infinite, and with that minus it goes to plus infinite. But anyway, you get an approximation of the Hankel function of order 0 for very small arguments, that is imaginary, negative, and almost infinite, very, very large. And so this formula is the low argument or a small radius approximation for the induced current. We can also make another approximation, that is the large argument approximation, when we have large argument. For example, when we evaluate the field at a very large distance. Remember the formulas for the electric field. The formulas for the electric field, apart from the Bessel functions depending on the radius, we have another Bessel function depending on beta times rho. Rho is the distance between the observation point and the z-axis. And in far field, this distance becomes very large, and we can make for very large beta rho, we can make a large argument approximation that is like this. Observe the attenuation with 1 over the square root of rho, and this is the attenuation that you expect for the electric field of a cylindrical source, infinite cylindrical source, and also the exponential phase. This is in fact a cylindrical wave in the far field. We substitute the large argument approximation of the Hankel function and get this summation now here in the far field, and we observe that we have the cylindrical wave here at the phase minus beta rho, amplitude 1 over square root of rho. This is normal for a cylindrical wave in the far field, and for the pattern of the cylindrical wave we have an infinite summation of a Fourier series in phi, that gives the dependence of the field with phi, that is the directivity or the pattern, the radiation pattern of the cylinder. We can use this formula for the electric field to compute the radar cross section that you know is proportional to the square root, sorry, not the square root, to the square of the absolute value of the electric field, and we obtain this equation for the two-dimensional radar cross section. We can make a small radius approximation also in the case that the cylinder has a very small radius. This is the radius much smaller than lambda. This is the same approximation that we did before, and we obtain the small radius approximation for the two-dimensional radar cross-section of the cylinder. And now, if we remind the formula for the radar cross-section of a three-dimensional cylinder approximately computed from the radar cross-section of the two-dimensional infinite circular cylinder, using that formula we can obtain an approximation of the radar cross-section in 3D for the three-dimensional cylinder of length L and a perpendicular incidence, provided that L is much larger than lambda. This is for the case L much larger than lambda and perpendicular incidence. We obtain this equation. So these are the equations that we obtained for the induced current. We have two cases, TM polarization and TE polarization, and at the top we have the general formula for the current as a function of phi. Phi is the position around the cylinder circumference, and below we have the approximation for a small radius, for electrical radius much smaller than the wavelength. As I said before, in the general case we have a Fourier series for phi angle of initially infinite terms. However, the coefficients become very small when the order n is larger than the argument ka. So we have to sum here, in this sum we have to sum up coefficients from approximately n equal to minus ka up to n equal to plus ka. So about 2 ka coefficients. If we want to have a smaller error, we can add a few more coefficients. So ka plus 5 or something like that could be enough. But the idea that I want to transmit is that you do not need to sum infinite coefficients or a very large number, only up to approximately order ka. In the case of a small argument, we only have the coefficient of order 0, that is a Hankel function that can be approximated by a logarithm, and the result is independent on phi. So the idea is that when the radius is small compared to the wavelength, the current is almost constant around the cylinder. The same in the TE case, but in the TE case the coefficients of the Fourier series for the general case depend on the derivative of the Hankel function. So for the small argument approximation we still have only the coefficient of order 0, but now the small argument approximation is not completely constant along phi, but almost constant along phi, because Ka is very small, so the second term, the term with the cosinus of phi, becomes very small compared to the first term, which is constant. So again we get, for a small argument, a current that is almost constant with respect to phi coordinate around the cylinder. We can see the plots of the current for different phi coordinates as a function of the phi coordinate around the cylinder. So it is the phi coordinate around the cylinder is, and for different radius in blue color we have the smallest radius, it is almost constant, and in, for example, here in magenta or violet color we have a very large radius of 100 lambda, and in this case what we observe is that the current is almost zero here. The current is almost zero here in that region, which is the region that is shadow with respect to the incident field. The incident field is in that direction, so we have electric field incident only on that part of the cylinder, but not here. So there is an illuminated region and a shadow region. We will see more about this later when we see high frequency techniques, but for the moment you can observe that when the radius of the cylinder is large compared to the wavelength, the current is almost zero in the shadow region and clearly different than zero in the illuminated region. The same for the TE case. However, for the TE case we observe the following. When the radius of the cylinder is not large enough, for example 1 lambda or 10 lambda, we still have current in the shadow region. It's small, but it's not completely zero. It's small compared with the current in the illuminated region, but not completely zero in the shadow region. Why? Because in the TE case we have the incident field that is transverse. It is in XY coordinates, so it produces an horizontal current, and the horizontal current flows around the cylinder and the current can reach the shadow region of the cylinder, the region that is not illuminated by the incident field. However, this current radiates. As we can see in the next slide, this current in the TE case that flows around the cylinder in the shadow region of the cylinder, it radiates. So we have radiation here. This current produces some radiation. So as it radiates, it loses power, and the power that is radiated, the current has less power as it radiates, so the amplitude of the current becomes smaller and smaller. That is what we can see, for example, here for the 1 lambda case or the 10 lambda case. We can see that the current decreases because it is radiating, and it decreases as it radiates. In the case of the case of TM polarization, we can see that the current converges to zero in the shadow region much faster. For example, for 1 lambda, we have a current in the shadow region, the TM case, that is smaller than the 10 lambda current, the current for radius 10 lambda in the TE case. And for the 10 lambda case, radius equal to 10 lambda in TM case, the current is almost the same as for radius 100 lambda. This is not the same in TE case. In the TE case, it is important to account for these currents that flow around the cylinder. In the TM case, the currents cannot flow around the cylinder because they are parallel to Z axis, so they flow in the up direction. They flow in the up direction, so they do not flow around the cylinder. This is due to the fact that the electric field is vertical and it produces vertical currents in the TM case, but in the TE case the electric field is horizontal and it produces horizontal currents. These horizontal currents in the TE case that flow around the cylinder in the shadow region are called creeping waves. They are called creeping waves. It is an important scattering effect, the presence of creeping waves in the TE case. We will see more about this in the high frequency, when we see high frequency approximations. It is important to note that all these effects are present only in high frequency. That is, when the radius of the cylinder is large compared to the wavelength, and large means 1 lambda or more. In the case of a small radius, for example 0.03 lambda or 0.1 lambda, we observe that the current is almost constant around the cylinder, and we cannot distinguish between the current in the illuminated region, that is called the physical optics current. More about this later in the high frequency techniques section of this chapter. In the case of small radius, we cannot distinguish between current in the illuminated region and creeping waves in the shadow region. Everything becomes mixed because we are not in the high frequency region. But for radius equal to 1 lambda or larger, we are in the high frequency region, and we can observe all these effects: the current, the physical optics current in the illuminated part of the cylinder, the creeping waves in the shadow region of the cylinder, etc. And it is interesting also to observe that the creeping waves travel in both directions. So the incident field from the bottom creates a creeping wave here that goes to the other side, but in the other side also the incident field creates a creeping wave that goes opposite to the first creeping wave. So we have two creeping waves with opposite propagation directions, and this creates a standing wave of current, a standing wave. And we can see here for 1 lambda the standing wave, and in the case of 10 lambda we can also see here some oscillation that is also the standing waves. So here we can you can see that this canonical solution provides a lot of insight on the scattering phenomena that are happening in the cylinder. This is one of the main uses of scattering analytical solutions for canonical geometries. The canonical geometries are too simple. Often in real life the geometry of the object is much more complex than a canonical geometry, and there are very few objects that have a geometry, a shape similar to canonical geometry, like a cylinder, a sphere, etc. However, the study of the canonical solutions or analytical solutions for canonical geometry allows us to have a lot of insight of the scattering phenomena. With regard to the equations for the total electric and magnetic field, these are the equations that we have obtained in the following the procedure of Balanis' book, and observe that we still have a summation of cylindrical harmonics. In fact, it is again in the form of a Fourier series in phi, and the parameters are the radius of the cylinder A and the distance of the observation, the distance of the observer to the z-axis rho, and again phi is the parameter, sorry, the variable of the Fourier series. And again, we don't need to sum infinite terms, only terms up to n equal to ka plus a small quantity like 5 or 3 or 10, depending on the accuracy that you want to get in the approximation to the infinite sum. But remember that you have to, as I said before, but I will write it down now for more clarity, you have to sum for n equal to minus ka to ka, and remember that you can just add a small quantity like 5 or something like that to improve the accuracy of the approximation to the infinite series. Okay, so this is, you program this, you can just sum up 2 ka terms plus 10 or something like that. And these are the formulas for the TE case. They are very similar, but we have some derivative of the Bessel functions. And if we plot the results first for a cylinder of a small radius, and later in the next slide cylinders of large radius, the radius here is small compared to the wavelength, and we have at the left the Tm result for polarization electric field parallel to the axis, cylinder axis, and in the TE polarization case we have the electric field parallel to the xy plane, so transverse to the cylinder axis. And it is important to observe the difference between these two cases. For a cylinder of a small radius, electrically a small cylinder, we observe that in the Tm case there is an incident plane wave in that direction, in x direction. There is some reflection here, and for that reason we can observe a standing wave, here standing wave, due to the reflection at the front of the cylinder. And after the cylinder we observe a shadow region due to the blockage of the incident field produced by the cylinder. But however, in the TE case, there is a very small amount of interaction between the incident field and the cylinder. Observe that there is still a standing wave, but it is with a very low standing wave ratio. It is like, it's like this, a very low standing wave ratio, because the reflected wave has a very slow amplitude, small amplitude compared to the amplitude of the incident field. And this is because there is in the TE case, the electrically small cylinder almost doesn't reflect a field. There is a very low reflection, and also there is no transmitted here. There is no transmitted, sorry, no shadow region. There is no shadow region, so almost no reflection, no shadow region. You can observe that the total field is, you observe the color scale, the total field is between 0.8 and maybe 1.4. So the standing wave ratio is less than 2 everywhere. And well, this means that there is a low interaction between the cylinder and the TE polarization incident field. However, there is a high interaction. But you already, in the TM case, but you already knew that, because you knew that when we have a grid of wires, a wire grid, remember? A grid of wire, if we have an incident field, if the incident field is parallel to the wires, the wire grid behaves as a reflector, as a solid plane, and it reflects the field, and we have a shadow region with zero field behind. Okay, so remember that we have a wire grid with an incident field parallel to the wires, the wire grid behaves as a planar plate, a solid plate, and it reflects the field and produces a shadow region behind. This is because there is a interaction. There is an interaction between the incident field and the wires parallel to the electric field, and this is the same that we can observe here. However, in the I want to erase this. I cannot erase this, but I can write it again. In the TE case, we have a wire grid and we have an incident field with polarization perpendicular to the wires. These are the wires. If the polarization is perpendicular to the wires, we know that the wire grid doesn't reflect the field, and the field crosses the wire grid. And this is because there is a low interaction between the wires and the electric field perpendicular to the wires. And this is the phenomena that we can observe here. Here we can observe that in the TE case, electrically small cylinder of radius small compared to the wavelength, produces a small amount of interaction, almost not perturbation. It almost doesn't perturb the incident field. If the radius wire was smaller, the perturbation would be also smaller. In the case of an electrically large cylinder, that is the radius of the cylinder much larger than the wavelength, the behavior is completely different. In this case, the slide shows the fields for a radius equal to 2 lambda, and 2 lambda is large for us. Even 1 lambda, a radius equal to 1 lambda for us, is large enough to observe these high frequency scattering effects. Here we can clearly observe the reflected field both in the TM case, a standing wave here, and in the TE case we also have a reflected field and a standing wave. So in both cases, TM and TE, the cylinder reflects the incident field back to the source, back to the source of the incident wave. So in this case, for a cylinder radius that is not small compared to the wavelength, we have also interaction in the TE case. Now, both cases, TM and TE, have a lot of interaction between the cylinder and the incident field. However, what is different between TM and TE, what is different is the shadow region. In the TM case, we have the shadow region. In the TE case, we don't have the shadow region, and this is due to the creeping waves. Remember what I said before, that in the TM case there are no currents here. The current is approximately 0 in the shadow region. So in this region, in the shadow region, the current is approximately 0, and so it cannot radiate in the shadow region, and we have a true shadow field approximately equal to 0 behind the cylinder. However, in the TE case, we have these creeping waves. Here for radius equal to 1 lambda are quite large. For radius equal to 2 lambda would be maybe not as large, but close. It would be something like that. It would be not as large as 1 lambda, but quite large anyway. And we will have radiation of these creeping waves. Remember that the creeping waves radiate field in the shadow region, so there is no longer a shadow behind the cylinder. So there is no shadow due to the radiation. This is due to the radiation of the creeping waves that are here behind the cylinder. These creeping waves radiate in the shadow region, so there is no shadow. And now in the far field we can compute the RCS in the far field we do the far field approximation of the total the scatter field. Here we have the total field in the TM case, the part corresponding corresponding to the scatter field is this, and in the TE case the part corresponding to the scatter field is this, and we can do the far field approximation of the Hankel function, and we obtain this. This is again a Fourier series in phi, where the coefficients of the Fourier series are given by the Bessel functions of argument Ka. A is the radius of the cylinder, and using this scatter field in the formula for the two-dimensional RCS, we have the scatter field square absolute value of the scatter field here. We get this equation for the radar cross section, and it is again the summation, the Fourier series summation. And remember that you only have to sum terms up to order Ka plus 5, for example, and in the negative side minus Ka minus 5 or something like that. And now when the radius of the cylinder is large compared to the wavelength, we can observe that this summation converges to pi a. So pi a is the high frequency approximation of the RCS of the cylinder, both in TE and TM cases. Both in TE and in TM cases, although in general in the general formula for any radius, the expressions of the Fourier series coefficients for the TM and TE case are different, but however in high frequency for radius very large compared to the wavelength, in practice it is enough that it is a few wavelengths, it converges to pi a. We can observe here the plot for the TM case for different cylinder radius. Blue color is the smallest cylinder radius, lambda over 20. This is very small. It is almost constant in frequency. We can see in the next slide that for radius much smaller than the wavelength, the small argument approximation of the Bessel functions gives this approximation for the RCS, and the RCS in the TM case for a small radius is almost constant in phi. So we can see here in blue color it is almost constant in phi. However, when the radius of the cylinder becomes large, it has a very characteristic shape given by a value almost constant in phi that is approximately equal. This is approximately equal to pi a here. This is pi a here. Pi a in this case for lambda, for a equal to 2 lambda, pi a is 6.3. So here we have 6.3. For a equal to lambda, pi a is 3.14. So here we have 3.14. So we have a constant value approximately equal to pi a in high frequency for almost all distances of observation except forward scattering. Here phi equal to 0. Phi equal to 0 is this forward scattering direction. It's forward scattering because the incident field comes also in the direction phi equal to 0. So clearly there is a very high peak of scatter field in the forward direction, and this is due to the fact that in the forward direction is in the shadow region, and the scatter field must cancel out the incident field, so the total field becomes approximately 0. So we need a strong peak of scattered field to cancel the incident field in the shadow region. And this is the reason why we have this peak here in the forward direction. But away from the forward direction, we have a almost omnidirectional scattering equal to pi a in high frequency. In the TE case, we don't have the shadow region, so we don't have the forward in the forward direction phi equal to 0. We don't have the high forward scattering peak, because there is no need to cancel the incident field to produce the shadow region. So the scatter field is the scatter field and the radar cross section is approximately constant for all observations of incidents except for a small radius. For a small radius, we have an important variation with a null, and we can observe here that in the small argument approximation of the Bessel functions, this small argument approximation leads to this formula for the small radius radar cross section that has a 1 minus 2 cosinus of phi dependence, so it has a null, and we can observe here the null. But except in this case of small radius, the RCS is quite constant with respect to phi. Here the radius is not very large, but we can observe the same behavior for larger radius. And it is approximately equal to pi a when the radius of the cylinder is not too small. We can observe here the dependence with a for the TM and TE cases, and we can observe that it is approximately equal to pi a. For example, here for a equal to 1 lambda, we have pi a equal to 3.14. For a equal to, for example, 0.5 lambda, we have almost 1.6, so it is pi over 2. So it is the high frequency approximation works quite well for radius larger than let's say lambda over 2 in the TE case, and maybe 0.2 lambda in the TM case, so it's quite good, the high frequency approximation. But interestingly, it increases linearly with A in the TM case, blue color, but it has some oscillation in the TE case that is in red color. We have this oscillation because we have the creeping waves from both sides of the cylinder that exit the opposite side, and these two waves, creeping waves that enter the shadow region in opposite sides of the cylinder, they propagate in opposite directions, and they form a standing wave of current in the shadow region. But also it is interesting to observe that the creeping wave, the scattering of the creeping wave here, we have the incident field, creates the creeping wave, and then it exits the cylinder, but there is an interference between the scattering from the creeping wave, the back scattering from the creeping wave, and the back scattering from the front illuminated surface. And this back scattering interference between the reflection between here the reflection at the front surface and the creeping wave scattering in the back direction, these interferences can be constructive or destructive. If it is constructive, we have here a peak of the TE cross section, and if the interference is destructive, we have a valley or local minimum of the TE radar cross section. So this is the reason for the oscillation, the interference between the scattering at the front illuminated surface and the scattering from the creeping wave, always in the back scattering direction. I say back scattering direction because this is a graph of monostatic This is a graph of monostatic RCS. Very important, monostatic RCS. So it's a backscattering case, and we see the graph versus the radius of the cylinder. So essentially, this graph just proves or shows us that the high frequency formula two-dimensional cross-section equal to pi a is quite good even for a small radius. In the case of a cylinder of a finite length, we have remember that the formula that if we have a cylinder of finite length, but the length is much larger than lambda. In practice, more than 1 lambda or 2 lambda is enough. And also, the direction of its incidence is perpendicular to the axis of the cylinder. Then we have this formula for the radar cross-section in 3D given the two-dimensional radar cross-section for the infinite circular cylinder times 2L square over lambda gives us the three-dimensional RCS. And this is the formula that we obtain in the general case for the three-dimensional monostatic RCS. This is the this is not the monostatic case, because here we have the variation with phi. So this is the formula for the biostatic RCS for a direction of observation phi and any radius of the cylinder A in the TM case and in the TE case for a finite length cylinder of length AL much larger or just larger than the wavelength. Another canonical geometry for which we have an analytical solution is the wedge. The wedge is formed by two semi-infinite planes, one plane along the x set plane, and the other has also in common with the first plane the z axis, but forms an angle 2 alpha with the x z plane. The edge of this wedge is the z axis here. So essentially we have the z axis as the edge, and then two planes semi-infinite, one along x direction and the other forming an angle twice alpha with x direction. If we see it from the top view, a view along z axis, we have here one plane in xz plane, and here the other plane forming an angle 2 alpha. The incidence direction is perpendicular to z axis, the same as in the circular cylinder. The two polarizations Tm and Te are defined with respect to z axis, again the same as in the cylindrical case. So in Tm the magnetic field is transverse to the z axis, so the magnetic field is parallel to xy plane, and the electric field is parallel to z axis, exactly the same as in the circular cylinder case. Similarly, in Te polarization we have the electric field transverse to z direction, that is along parallel to xy plane, and the magnetic field parallel to z axis. The incidence direction is perpendicular to z axis and forms an angle psi prime with respect to xz plane. So this psi prime angle is the incidence angle. The observation angle is phi, the same phi in cylindrical coordinates, and the observation distance to z axis is rho, the same, the usual cylindrical or polar coordinates. The equations for the electric and field in Tm case and the magnetic field in the Te case at the following. This is the electric field in the TM case and the magnetic field in the TE case. We still have a summation of cylindrical harmonics. It is a Fourier series in phi. In the TM case, it is a sinus Fourier series, and in the TE case, it is a cosinus Fourier series in phi. Phi prime is the incidence direction, it is a parameter. Rho is the observation distance, it is also a parameter of the Fourier series. It is interesting to note that the order of the harmonics in the Fourier series that is equal to the order of the Bessel function, the order of the harmonics is non-integer. The order of the harmonics depends on the wedge angle alpha, and it is a fractional number. It is a rational number. It is not integer number. It doesn't matter. You can define here in the same way a Fourier series. The only thing is that now the Bessel functions are not of integer order, they are of rational order, but it doesn't happen. It works the same. And here we have the total field, incident plus scatter, for two wedges. One has inner angle 2 alpha equal to 0 degrees, so in fact it is a semiplane, and the other has an inner angle of 90 degrees, so it is a right angle wedge. It's like this. So this is the wedge here. So this is metal, and in the 0 degrees case the wedge is this here, and then sorry, there is no metal. So what we have here, the incidence field, direction of incidence is 30 degrees. So here we have incidence field at 30 degrees. We have reflected field. The incident field plus the reflected field create a standing wave here. This is the standing wave. In this area we don't have reflected field, so in this area here we only have incident field. Here only incident field. And in this area we have the shadow. We have the shadow here. And between the shadow and the region with incident field, we have a transition region where there is some diffraction at the edge. It is interesting to observe that the shadow is not hard. The shadow is soft, because there is this transition, this soft transition, due to diffraction at the edge. And this is what you can compute using the high frequency techniques for edge diffraction, the diffraction coefficients, etc. More about this later in the latest video of the course. And you can compute, remember that there are techniques and tables and graphics to compute the fields in this region due to diffraction. We have a very similar pattern of the field in the 90 degrees case. We have the reflection, the standing wave due to the reflection, and the summation of the incident field plus the reflected field produces the standing wave. Then we have the area here with only incident field, the transition to the shadow region here, and this is not shadow because this is the wedge. The wedge has an inner angle of 90 degrees, so this is perfectly conducting object. This is metal, perfect conductor, so zero fields here. Here we have zero fields, almost zero, due to shadow, and then we have the transition to the region with the incident field. In the TE case, we have the incident field, incidence direction is the same, 30 degrees. We have the reflected field, we have the standing wave, we have here the region with the incident field. Everything is the same except the shadow. We don't have shadow in the TE case. This is the same as in the circular cylinder. These are not strictly creeping waves, but these are a kind of creeping wave. In fact, they turn around the edge. They turn around the edge. They are traveling surface wave along the shadow region in the perfectly conducting plane, here or here, and they radiate. And since they radiate, they produce these fields in the shadow region here. They produce fields in the shadow region. This is the zero field in the inside of the wedge that is perfectly conducting. So again, we have this soft transition from the incident field to the zero inside the wedge. And this case is due to the radiation of the creeping waves. And we can also compute this in high frequency, using high frequency techniques, using the diffraction coefficients for computing edge diffraction. And the last case that we consider is the sphere, the perfectly conducting sphere. Radius of the sphere is A. This is the formula of the three-dimensional radar cross-section of the sphere. Now the sphere is a three-dimensional object. It's not a two-dimensional infinite object like the circular cylinder or the wedge. The sphere is already three-dimensional. This is the formula for the radar cross-section. Again, we have a summation of Bessel functions. The summation up to, as always, up to Ka. We sum up to n equal to Ka plus a small number, for example 5 or something. The larger this constant that you add to Ka, the better approximation to the sum, to the infinite sum, to the sum of infinite terms. And it is interesting to observe that these Bessel functions are spherical Bessel functions. And spherical Bessel functions are a function of the usual Bessel functions of rational order equal to integer plus 1/2. It is just interesting. You can find all the information about, all the information about spherical Bessel functions in the Bessel functions appendix of Balanis' book. You can do a low frequency approximation for a small radius much smaller than lambda. It turns out that the radar cross section is now proportional to A over lambda to power 6. So if we plot the radar cross-section versus A over lambda, compare normalized to the high frequency result by A squared, we find that for radius much smaller than lambda, the radar cross-section grows very fast with A over lambda, as fast as power 6, A over lambda to power 6. So this is what we can observe here in the low frequency approximation. This is what is called Rayleigh scattering. This is the scattering of particles that are very small compared to lambda. And in high frequency the radius is much larger than lambda, so we do a large argument approximation of the Bessel functions and obtain this, and it can be proved that this infinite summation is times lambda squared over 4 pi is equal to pi A squared. This is the projected area, and this is the high frequency. This is the high frequency approximation to the radar cross section. This is the value that we already obtained. Remember that when we were discussing radar cross section, the value that we obtained in here, the value that we obtained for a sphere was pi a squared. This was just an approximation, intuitive approximation, but it is in fact the high frequency value. We will study more in detail high frequency methods in the next video, but for the moment you already know that if we get the analytical exact solution for the spherical canonical geometry, the exact solution, and we do the large argument approximation for a much larger than lambda in the Bessel functions, what we obtain in fact is exactly pi a, exactly the approximation, the high frequency approximation of the radar cross section. We can observe how the radar cross section converges to pi a. Remember that here the vertical axis we have the radar cross section normalized to pi a square, so you can see how it converges to pi a square. And it is not far away. For example, if the radius is larger than, for example, 1, you can observe that it is not far from the high frequency value of pi a. So here we finish with canonical and analytical solutions for canonical geometries, and in the next video we will start with high frequency methods.